Imagine looking across almost the entire history of the universe and finding a lighthouse switched on before the cosmos had finished building its first cities of stars. That is the promise of a remarkable new Euclid result, a quasar so ancient that its light began traveling toward us when the universe was only a tiny fraction of its present age. This is not simply a story about a distant bright point. It is a story about how darkness became structure, how black holes grew with astonishing speed, and how a survey telescope designed to map invisible dark matter can also uncover some of the universe's earliest, most extreme engines. Let us begin with the word quasar. A quasar is the blazing center of a galaxy powered by a supermassive black hole. The black hole itself is dark, but matter spiraling into it forms a superheated disk. Friction, magnetic fields, and violent jets can release more energy than all the stars in the host galaxy combined. The light from a quasar is therefore a message from an engine. The farther away the quasar is, the longer that message has been traveling. And because light has a finite speed, telescopes are also time machines. When we observe a very distant object, we see it not as it is today, but as it was when its light began its journey. Euclid is especially good at finding these cosmic messages. The European Space Agency's spacecraft scans enormous areas of sky in visible and near-infrared light. Its main mission is to understand dark energy and dark matter by measuring the shapes and distribution of billions of galaxies. But a wide survey has an unexpected advantage. Rare objects are easy to miss when you stare at one small patch of sky. Euclid instead acts like a net cast over the cosmos. Even a tiny population of ancient quasars has a better chance of being caught when the net covers a vast region. The newly reported quasar belongs to an era when the universe was still young, less than 1 billion years after the Big Bang. In cosmic terms, that is barely the opening scene. The first galaxies were assembling, the first generations of stars were forging heavier elements, and the universe was emerging from a long period of darkness. Yet this quasar was already bright enough to announce itself across billions of light-years. Its central black hole must have been massive, and it must have been feeding rapidly. That immediately raises a difficult question: how can a black hole become enormous so early? Black holes grow by swallowing matter, but growth is not unlimited. Gas has to lose energy and angular momentum before it can fall inward. As the gas heats up, it shines. That radiation pushes outward, resisting the inflow that feeds the black hole. There is a theoretical speed limit known as the Eddington limit. It is not an absolute wall, but it describes the balance between gravity pulling material in and radiation pushing material away. If a black hole begins from a small seed and grows near this limit, the universe has only a limited amount of time to make it supermassive. That is why ancient quasars are so valuable. They test competing ideas about the first black hole seeds. Perhaps the seeds were the remnants of the universe's first massive stars. Such seeds would begin with tens or hundreds of solar masses and need extraordinary growth. Another possibility is direct collapse. Under special conditions, enormous clouds of primordial gas may have collapsed almost directly into black holes thousands or even millions of times more massive than the Sun. Starting with a heavier seed makes the early growth problem much easier. A third route involves rapid mergers. The first galaxies lived in a dense cosmic environment. Their black holes could collide as galaxies merged, building mass in steps. But mergers also produce gravitational waves and should leave clues in the surrounding stellar populations. The Euclid discovery does not, by itself, choose one explanation. It provides a new target and a sharper statistical constraint. To understand the object, astronomers must measure its redshift, its chemical fingerprints, its host environment, and the speed at which it is consuming gas. Redshift is the key to cosmic distance. As the universe expands, the wavelengths of traveling light are stretched. Light that began ultraviolet may arrive shifted into visible or infrared wavelengths. The amount of stretching tells astronomers how long the journey has lasted and therefore how far back in time they are looking. Euclid's images can identify a promising candidate, but discovery is only the first act. Follow-up observations from ground-based observatories and space telescopes can spread the quasar's light into a spectrum. A spectrum is like a barcode. It reveals emission lines from hydrogen, carbon, oxygen, and other elements, while also confirming how strongly the universe has stretched the light. The surrounding universe matters too. Ancient quasars do not live in isolation. Their immense energy floods nearby gas with radiation. That radiation can carve ionized bubbles through the young universe, helping end the cosmic dark ages in a process called reionization. During the first few 100 million years, neutral hydrogen filled much of space and absorbed certain wavelengths of light. As young stars and quasars produced ultraviolet radiation, they gradually stripped electrons from that hydrogen. The universe became transparent to more kinds of light. A bright ancient quasar is therefore both a beacon and a disturbance. It lets us inspect the material between galaxies, while simultaneously changing that material. By examining absorption features in the quasar's spectrum, scientists can estimate how much neutral hydrogen lies along the line of sight. The discovery also helps map the cosmic neighborhood of the quasar. If the object is surrounded by an overdense region, it may have formed in one of the early locations where matter was already gathering faster than average. That would support the idea that the first supermassive black holes grew in unusually rich environments. But there is a caution hidden inside every headline about the most ancient object. Astronomy is a science of measurements and uncertainties. The record belongs to the object whose distance has been most securely established, and new observations can revise the ranking. Even so, records are not the real point. The deeper value is the growing sample. One ancient quasar can be an anomaly. A population of them can reveal how common rapid black hole growth was, how quickly galaxies assembled, and whether the standard picture of cosmic history needs adjustment. Euclid's contribution is especially powerful because it is designed for scale. Its wide field does not replace the exquisite depth of the James Webb Space Telescope, nor the specialized X-ray and radio eyes of other observatories. Instead, Euclid finds the rare coordinates where those instruments should look next. Think of it as a cosmic surveyor working ahead of a team of detectives. Euclid draws the map. Webb studies the host galaxy in infrared detail. X-ray observatories probe the hot corona around the accretion disk. Radio telescopes search for jets and magnetic structures. Together, they can reconstruct the quasar's life. There is another reason this matters. The same physics that makes a quasar visible can also influence galaxy evolution. Black hole outflows may heat or expel gas, suppressing the formation of new stars. In other cases, shocks from the outflow can compress clouds and trigger star formation. So the relationship between a young galaxy and its central black hole may be less like a quiet partnership and more like a feedback loop. The galaxy supplies gas to the black hole. The black hole releases energy that reshapes the galaxy. Over billions of years, each may help determine the fate of the other. The ancient Euclid quasar gives scientists a glimpse of that relationship near its beginning. We are not seeing a mature galaxy with a black hole settled in the center. We are seeing a system still under construction, when the rules of growth were being tested in real time. And the discovery arrives at an important moment for cosmology. Wide surveys are becoming capable of combining images, spectra, gravitational lensing, and time-dependent behavior across enormous areas. The universe is no longer being studied only as a collection of individual photographs. It is becoming a measurable network of structure. Galaxies trace the web of matter. Dark matter shapes their paths. Dark energy changes the expansion of space. Quasars illuminate the spaces between galaxies. Every rare object becomes a marker in a much larger story. As Euclid continues its survey, more ancient quasars may appear. Some could be fainter, some more distant, and some living in environments unlike anything we have seen. A larger sample may reveal that the first black holes grew in many different ways rather than following one universal recipe. It may also reveal surprises. Perhaps some black holes formed from unexpectedly heavy seeds. Perhaps the earliest galaxies were more efficient at feeding them than current models predict. Or perhaps selection effects have made the early universe look more extreme than it truly was. That is the healthy tension at the heart of discovery. A telescope does not merely confirm what we already believe. It gives nature a chance to disagree. When a tiny, ancient light source forces us to rethink how structure formed, the object becomes more than a record holder. It becomes a question written across cosmic time. For now, the quasar's light continues to arrive. Every photon is a survivor of an ancient journey, released before Earth, before the Sun, and before the Milky Way reached its modern shape. It crossed expanding space, passed through clouds of primordial gas, and finally met a mirror in orbit around our planet. In that meeting, a distant black hole becomes part of our present. Euclid has not opened a door into the past so much as shown us that the past is still arriving, frame by frame, in the quiet light of the sky. The universe was young, but it was not simple. It was already building galaxies, igniting quasars, sculpting invisible structure, and preparing the cosmic architecture we see today. The ancient Euclid quasar is one more sign that the opening chapters of the universe were faster, brighter, and stranger than we once imagined. And somewhere in the next sweep of Euclid's survey, another impossible lighthouse may be waiting.